Right now, you are sitting on a rock hurtling through space at 670,000 mph. That rock orbits a nuclear furnace 1 million times its size. That furnace is one of 400 billion stars spinning through a galaxy so vast that light itself needs 100,000 years to cross it. But here is what will shatter your mind. Our entire galaxy, with all its billions of worlds and countless civilizations that might exist, is nothing more than a single grain of sand in an ocean containing 2 trillion other grains. Picture yourself standing in the middle of New York City at midnight. The lights stretch endlessly in every direction. Buildings fade into darkness at the horizon. Now imagine that cityscape extending not just to the next state, but across the entire continental United States. Then stretch it across the Pacific Ocean to Asia. Keep stretching it around the entire Earth. Then multiply that distance by 6 billion. You have just visualized the width of our galaxy. Scientists confirmed through precise measurements that the Milky Way spans 100,000 light-years from edge to edge. 1 light-year equals 6 trillion miles. This means our galactic home measures 600,000 trillion miles across. Writing out that number would require a line of zeros stretching from your house to the nearest grocery store. But here lies the first shock to human intuition. Despite this mind-crushing scale, our galaxy represents merely the first step in a cosmic ladder that climbs toward infinities our brains cannot process. Every single point of light you see twinkling in the night sky belongs to our galactic neighborhood. The fuzzy band of stars cutting across dark skies reveals the edge-on view of our spiral arms. We live inside this cosmic city embedded within its structure like a single cell inside a massive organism. From our position roughly 26,000 light-years from the galactic center, we can observe star formation regions where new suns ignite. Every year we witness stellar nurseries where gravity sculpts gas clouds into burning spheres. Ancient red giants expire in spectacular explosions that seed space with heavy elements. Yet what makes this scale truly disturbing is not its size, but what it represents. Our galaxy forms just one unit in a hierarchy of structures that grows increasingly vast and incomprehensible. Each level of cosmic organization dwarfs the previous one by factors that render human experience meaningless. Standing on Earth and contemplating galactic distances feels like an ant trying to comprehend the size of North America. The ant can sense that something vast exists beyond its immediate surroundings, but lacks the cognitive framework to grasp continental scales. Humans face the same limitation when confronting cosmic distances. Light moves faster than anything else in the universe. Nothing can outrun a photon racing through the vacuum of space. At 670 million miles per hour, light circumnavigates Earth 7 times in a single second. This cosmic speed limit represents the fastest possible way to traverse distances in our reality. Yet even light, the ultimate speedster of physics, requires 100,000 years to travel from one edge of our galaxy to the other. Think about what this means for human perspective. The light leaving distant stars in our galaxy tonight began its journey when early humans first learned to make fire. Photons now reaching Earth from the far side of the Milky Way started traveling before written language existed. These ancient light particles carry information about stellar events that occurred when our ancestors were still discovering agriculture. Scientists use this light travel time as a cosmic measuring stick. When astronomers observe distant galactic regions, they see them as they existed thousands of years ago. The galaxy we observe tonight is actually a patchwork of different time periods. Nearby stars show us recent events. Distant stellar neighborhoods reveal ancient history. We never see our galaxy as it exists right now, but rather as a time-averaged composite spanning millennia. But this journey time becomes even more mind-bending when we consider galactic rotation. Our entire galaxy spins like a cosmic pinwheel. The solar system orbits the galactic center once every 200 million years. During light's journey across our galaxy, the entire structure completes nearly half a rotation. The galaxy literally changes shape while light travels between its regions. Even more disturbing is what this implies about cosmic communication. Any attempt to send signals across our galaxy faces this fundamental barrier. Radio waves and laser beams travel at light speed, meaning galactic communication requires patience measured in geological time. If an alien civilization on the far side of our galaxy sent us a message today, our great-great-grandchildren would need to wait for our great-great-grandchildren to receive it. This communication barrier means that our galaxy can never function as a unified system. Different regions operate independently, isolated by the fundamental speed limit of information transfer. What appears to be a single cosmic structure actually consists of countless independent zones, each evolving without knowledge of distant galactic neighborhoods. Step outside on a clear night and locate the brightest star in the sky. That brilliant point of light is Sirius, burning 25 times brighter than our Sun. It appears so luminous that ancient civilizations based their calendars on its movements. To your eyes, Sirius seems close enough to reach with a sufficiently tall ladder. The confirmed reality shatters this illusion completely. Sirius lies 8.6 light-years away from Earth. This distance equals 51 trillion miles. If you could drive a car at highway speeds toward this nearest bright star, the journey would require 300 million years. But Sirius is practically next door compared to typical galactic distances. Most stars in our galaxy are separated by gaps so vast they defy human comprehension. The average distance between neighboring stars measures 4 light-years. In cosmic terms, this represents an almost perfect vacuum, punctuated by occasional tiny islands of matter. To visualize this emptiness, imagine shrinking our solar system until the Sun becomes the size of a basketball. At this scale, Earth would be a grain of sand orbiting 26 feet away. The nearest star would be another basketball located in a different city, perhaps Denver if you started in New York. Everything between these basketballs contains essentially nothing but empty space. This emptiness creates profound implications for space travel between stars. Even traveling at the speed of light, journeys to nearby stars require years. Conventional spacecraft moving at achievable speeds would need tens of thousands of years to reach the closest stellar neighbors. The vast majority of our galaxy remains forever inaccessible to human exploration. The void between stars also explains why alien contact seems so unlikely despite the enormous number of potential worlds. If alien civilizations exist on planets orbiting distant stars, they face the same fundamental barriers of space and time that isolate us. The universe conspires to keep intelligent species separated by gulfs too wide for meaningful interaction. Scientists have calculated that our galaxy contains roughly 400 billion stars, yet these countless suns are sprinkled so sparsely throughout galactic space that each one exists in splendid isolation. The night sky creates an optical illusion, making stars appear crowded together when they actually inhabit a realm of cosmic loneliness. Imagine counting every star in our galaxy. Begin with the Sun and work your way outward through the spiral arms. Count each red dwarf, each blue giant, each binary system spinning through space. Maintain a steady pace of 1 star per second without stopping to sleep or eat. You would finish counting after 12,600 years. Confirmed observations by space telescopes reveal that our galaxy contains between 100 billion and 400 billion stars. The exact number remains uncertain because dust clouds block our view of distant galactic regions. Dark nebulae hide stellar populations that we can detect only through infrared radiation. But even the conservative estimate of 100 billion stars overwhelms human comprehension. Each of these stellar furnaces burns with the power of nuclear fusion. Every second, our Sun converts 4 million tons of matter into pure energy. Multiply this output by hundreds of billions of similar reactions occurring simultaneously throughout our galaxy. The total energy production of the Milky Way exceeds the power consumption of human civilization by factors that require scientific notation to express. Yet this staggering stellar population creates an unsettling realization. Despite containing enough suns to power quadrillions of civilizations, our entire galaxy represents a minuscule fraction of cosmic existence. Astronomers classify the Milky Way as a medium-sized spiral galaxy. Larger galaxies contain more than 1 trillion stars. Smaller dwarf galaxies harbor only a few billion stellar furnaces. The probability mathematics surrounding galactic star counts suggests mind-bending possibilities for planetary systems. If even 1% of galactic stars host Earth-like worlds, our galaxy contains billions of potentially habitable planets. Some of these worlds might harbor civilizations far older and more advanced than human society. Others might contain life forms so alien that we lack vocabulary to describe them. But what makes these numbers truly disturbing is their cosmic insignificance. Every star we have ever observed, every planet we might discover, every possible alien civilization that might exist within our galactic borders, amounts to less than 1% of the matter in the observable universe. Our galaxy, with all its countless worlds, represents a single grain of sand on an infinite beach. Look toward the constellation Andromeda on any autumn night. That faint smudge of light appears unremarkable among the surrounding stars. Ancient astronomers catalogued it as a nebula, assuming it belonged to our local cosmic neighborhood. Modern telescopes reveal a truth that should terrify and inspire in equal measure. You are looking at another galaxy containing over 1 trillion stars. The Andromeda galaxy stretches 220,000 light-years across, making it more than twice the diameter of our Milky Way. This galactic giant harbors enough stellar furnaces to dwarf our local star count by factors of 3 or 4. If our galaxy is New York City, Andromeda represents the entire eastern seaboard of the United States. But confirmed measurements reveal something even more remarkable. Andromeda is racing toward us at 250,000 mph. This cosmic collision course will culminate in the most spectacular event our solar system will ever witness. Computer simulations show that in 4.5 billion years, these two galactic titans will merge in a gravitational dance lasting several billion years. The collision will reshape both spiral structures into a single elliptical galaxy that astronomers have already nicknamed Milkomeda. During this merger, our solar system will likely survive intact. The vast spaces between individual stars mean that stellar collisions remain extremely unlikely even during galactic impacts. Instead, gravitational forces will fling our Sun and its planets into new orbits around the combined galactic center. Yet what makes Andromeda truly mind-bending is not its size or approaching collision, but what it represents about cosmic distances. The light you see from Andromeda tonight began its journey 2.5 million years ago, when those photons started traveling toward Earth. Early human ancestors were just learning to use stone tools. The galaxy you observe existed before modern humans evolved. This temporal displacement means we can never see Andromeda as it exists today. We observe its ancient past preserved in light that has traveled across the cosmic void for millions of years. The galaxy approaching us right now might look completely different from what we observe through telescopes. Between our galaxy and Andromeda stretches a void containing almost nothing but dark matter and scattered gas clouds. This intergalactic space harbors temperatures near absolute zero and densities lower than the best vacuum chambers humans can create. Yet this seemingly empty gulf teems with invisible forces that govern galactic motions across cosmic time. Our galaxy does not drift alone through cosmic space. The Milky Way belongs to a gravitational family called the Local Group, containing over 50 individual galaxies locked in an eternal cosmic dance. This galactic neighborhood spans roughly 10 million light-years and harbors enough combined mass to bend space and time across vast distances. Confirmed observations reveal that most galaxies in our local group are dwarf systems containing only a few billion stars each. These cosmic midgets orbit around the two dominant spiral galaxies, our Milky Way and the approaching Andromeda. Like planets circling a binary star system, these smaller galaxies follow complex orbital paths determined by the gravitational interplay between the two largest group members. Scientists have discovered that our galaxy is actively cannibalizing its smaller neighbors. Tidal forces created by the Milky Way's immense gravitational field strip stars and gas from nearby dwarf galaxies, feeding material into our galactic disk. This cosmic feeding process has continued for billions of years, with our galaxy growing larger by consuming nearby dwarf systems. But this galactic predation reveals something profound about cosmic evolution. Galaxies do not exist as isolated islands floating through empty space. They inhabit gravitational communities where constant interactions shape their structure and evolution. The peaceful appearance of night sky galaxies masks violent processes that unfold over cosmic time scales. Galaxy clusters represent the most massive gravitationally bound structures in the universe. These cosmic cities contain thousands of individual galaxies held together by forces so powerful they distort space and time across millions of light years. The nearest major cluster, called Virgo, contains over 1,300 galaxies and lies 54 million light-years from our local group. Confirmed measurements reveal that galaxy clusters should not exist according to the visible matter we observe. The combined gravitational pull of all stars and gas in cluster galaxies cannot account for the tremendous forces needed to hold these structures together. Galaxies within clusters move at speeds approaching 3 million mph. Such velocities should have scattered cluster members across cosmic space billions of years ago. The solution to this puzzle required discovering that most cluster mass remains completely invisible. Dark matter outweighs visible stars and gas by ratios of 10:1 throughout galaxy clusters. This mysterious substance reveals itself only through gravitational effects on light and matter, creating a cosmic scaffolding we can map but cannot directly observe. Scientists use gravitational lensing to study dark matter distribution in galaxy clusters. Massive clusters bend space so severely that they act like cosmic magnifying glasses, distorting the appearance of background galaxies. The amount of distortion reveals how much invisible mass clusters contain. Most spectacular example of dark matter evidence comes from the Bullet cluster, where two galaxy clusters collided at speeds exceeding 10 million mph. During this cosmic collision, the visible gas clouds interacted and slowed down, but the dark matter components passed through each other unchanged. Gravitational lensing maps show dark matter and visible matter separated by millions of light years, providing direct proof that invisible mass exists independently of stars and gas. Superclusters represent the largest confirmed gravitational structures in our universe. These cosmic formations stretch across distances so vast that light requires hundreds of millions of years to traverse them. Our local group belongs to the Laniakea supercluster, a gravitational collection spanning 500 million light-years and containing over 100,000 galaxies. The discovery of superclusters revolutionized our understanding of cosmic organization. Instead of being randomly scattered through space, galaxies arrange themselves in vast networks connected by filaments of dark matter and gas. These cosmic highways channel matter across distances that dwarf individual galaxy clusters, creating a hierarchical structure that extends to the largest observable scales. Scientists mapped our local supercluster by tracking the peculiar motions of thousands of galaxies. Despite cosmic expansion pushing distant galaxies apart, gravity causes nearby galaxies to move toward regions of higher density. By measuring these gravitational flows, astronomers revealed that our Milky Way and millions of neighboring galaxies are all streaming toward a massive gravitational attractor. This attractor, called the Great Attractor, contains the combined mass of tens of thousands of galaxies concentrated in a region obscured by dust clouds in our galactic plane. The gravitational pull from this cosmic monster influences galaxy motions across hundreds of millions of light years, creating currents in the cosmic web that carry entire galaxy clusters toward areas of increasing density. Step back far enough from the universe and a stunning pattern emerges. Galaxies do not scatter randomly through space, but organize themselves into a vast three-dimensional network, resembling soap foam floating in cosmic darkness. This structure, called the cosmic web, represents the largest scale organization of matter in our universe. Computer simulations confirm that this web-like architecture formed naturally through gravitational processes beginning shortly after the Big Bang. Dark matter started clumping together when the universe was only a few 100,000 years old, creating gravitational seeds that eventually grew into the cosmic scaffolding we observe today. The cosmic web consists of 4 distinct components working together across billions of light years. Dense nodes mark the intersections where galaxy clusters form. Filaments stretch between nodes like cosmic highways, channeling matter across vast distances. Walls form sheet-like structures where filaments intersect. Between these structures lie cosmic voids containing almost nothing but empty space. Scientists have mapped this cosmic architecture by observing millions of galaxies and measuring their 3-dimensional positions in space. The resulting surveys reveal that galaxies trace out the edges of enormous bubbles, with void regions occupying bubble interiors. This foam-like structure extends throughout the observable universe with remarkable consistency. The scale of cosmic web components defies human intuition. Individual filaments stretch across hundreds of millions of light years while maintaining widths of only 20 million light years. These cosmic threads appear impossibly thin when viewed at universal scales, yet they contain enough matter to fuel billions of galaxies. Imagine a sphere of space 300 million light-years across containing almost nothing. No galaxies shine within this cosmic desert. No stars illuminate its darkness. No planets orbit through its void. This empty realm, called a cosmic void, represents one of the most mysterious regions in our universe. The Brotes void, discovered in 1977, spans 330 million light-years in diameter, while containing fewer than 60 known galaxies. If our local group existed within this cosmic bubble, the nearest major galaxy would lie so far away that it would appear as a barely detectable smudge in our most powerful telescopes. Confirmed observations reveal that cosmic voids occupy roughly 80% of universal volume. These enormous empty regions separate the cosmic web filaments where galaxies cluster together. Despite their vast size, voids contain less than 15% of the average matter density found elsewhere in the universe. Point the most powerful telescope ever built toward any tiny patch of apparently empty sky. Keep the camera open for days, collecting every photon that arrives from that cosmic direction. The resulting image will reveal something that should fundamentally change how you think about existence. That tiny region, no larger than a grain of sand held at arm's length, contains thousands of galaxies. The Hubble Ultra Deep Field, created by combining 800 separate images with 11 days of total exposure time, revealed over 10,000 galaxies in a patch of sky covering just 1/13 millionth of the celestial sphere. Each galaxy in this cosmic census contains billions of stars, many likely hosting planetary systems where life might exist. Confirmed analysis of deep field observations allows astronomers to calculate the total galaxy population within our observable universe. The most recent estimates based on data from the Hubble and James Webb Space Telescopes suggest that 2 trillion galaxies populate the cosmic volume we can currently detect. 2 trillion represents a number that overwhelms human comprehension. If you could observe one galaxy per second without stopping, you would need 63,000 years to see them all. Each of these galactic islands contains its own stellar populations. Conservative estimates suggest that the average galaxy harbors 100 billion stars. Multiplying galaxy count by stellar populations yields a cosmic census exceeding 10 to the 24th power individual stars. This number surpasses the count of grains of sand on every beach on Earth. Walk along any ocean shoreline and scoop up a handful of sand. Count the individual grains between your fingers. A typical handful contains roughly 10,000 tiny fragments of rock and shell, each grain representing millions of years of erosion and weathering. Now expand your count to encompass every beach on Earth. Include the Caribbean islands, the Mediterranean coast, the Pacific atolls, and the Arctic shores. Scientists estimate that Earth's beaches contain approximately 7 quintillion grains of sand. This astronomical count of earthly sand grains pales in comparison to cosmic stellar populations. Confirmed observations reveal that the observable universe contains more stars than grains of sand on Earth. The 2 trillion galaxies we can detect harbor enough stellar furnaces to dwarf our planetary sand count by factors of thousands. The universe you can see tonight has boundaries, not physical walls marking the end of space, but fundamental limits imposed by the speed of light and the age of cosmic time. These boundaries define what astronomers call the observable universe, a sphere of space containing everything we can potentially detect using any technology humans might ever develop. Confirmed measurements reveal that this observable sphere measures 93 billion light-years in diameter. This distance represents the maximum extent of space from which light has had time to reach Earth since the universe began. Beyond this cosmic horizon lies a realm forever hidden from human observation. At the very edge of observable space glows a wall of ancient light, marking the boundary between visible cosmos and unknowable void. This cosmic microwave background radiation represents the oldest light in the universe, emitted when atoms first formed, and space became transparent 13.8 billion years ago. Before this moment, called recombination, the universe contained too much free energy for stable atoms to exist. Protons and electrons remained separated in a cosmic soup so dense that light could travel only microscopic distances before scattering off charged particles. The universe was literally opaque, like being inside a glowing fog so thick that nothing could be seen beyond arm's length. When cosmic expansion cooled temperatures below 3,000 degrees, protons and electrons combined into hydrogen atoms for the first time. This removed the charged particles that scattered light, allowing photons to travel freely through space. The universe became transparent in a cosmic instant, releasing radiation that continues traveling toward us today. Something invisible is tearing the universe apart. Dark energy, comprising 68% of cosmic contents, accelerates the expansion of space with a force so powerful that it overwhelms gravity across distances larger than galaxy clusters. This mysterious component of reality pushes distant galaxies away from us at ever-increasing speeds. The discovery of cosmic acceleration shocked astronomers who expected gravitational forces to gradually slow universal expansion. Two independent research teams studying distant supernovae in 1998 found that cosmic expansion was speeding up rather than slowing down. This observation earned the 2011 Nobel Prize in Physics and revolutionized our understanding of cosmic evolution. Dark energy behaves unlike any known form of matter or radiation. While normal matter becomes less dense as space expands, dark energy maintains constant density throughout cosmic growth. This means that dark energy's influence grows stronger over time as space increases in volume, while dark energy density remains unchanged. Most galaxies visible in tonight's sky will vanish from human view within the next 2 trillion years. Dark energy acceleration will carry these cosmic neighbors beyond our observational horizon, leaving future astronomers with an almost empty night sky containing only galaxies within our local group. Earth occupies the exact center of the observable universe. This statement appears to place humanity in a special cosmic position reminiscent of ancient geocentric beliefs. Yet this central location results not from cosmic design, but from the fundamental physics of observation and light travel time. Every observer in the universe sits at the center of their own observable sphere. The observable universe is defined as the region from which light has had time to reach a specific location since cosmic time began. This creates a personal cosmic horizon centered on each observer's position, making every location the center of its own visible cosmos. Theoretical physics suggests that our entire observable universe, containing 2 trillion galaxies across 93 billion light-years, might be smaller than a subatomic particle within a vastly larger cosmic structure. This mind-shattering possibility emerges from models proposing infinite hierarchies of organization, extending far beyond anything humans can observe or imagine. You are reading these words on one planet orbiting one star in one galaxy, among 2 trillion cosmic neighbors, scattered throughout an observable universe that might be smaller than an atom in ultimate reality. This perspective places human existence within a context so vast it challenges every assumption about significance, purpose, and cosmic importance. Earth measures roughly 25,000 miles around, a tiny rock spinning through space at 67,000 mph around a nuclear furnace that consumes 4 million tons of matter every second. Our Sun ranks as a perfectly average star among 400 billion stellar furnaces populating our galactic neighborhood. The Milky Way galaxy spans 100,000 light-years while containing enough stellar material to power quadrillions of civilizations. Yet our entire galactic home represents just one grain of sand on an infinite cosmic beach, containing more galaxies than grains of sand on every beach on Earth. This cosmic perspective simultaneously renders human existence infinitesimally small and profoundly meaningful. We represent temporary patterns of organized matter that achieved the remarkable ability to contemplate cosmic scales far beyond our evolutionary origins. Humanity developed from simple chemical processes on one small planet, yet we have discovered cosmic structures spanning billions of light years. Every atom in your body except hydrogen was created inside a star that lived and died before our solar system formed. The calcium in your bones, the iron in your blood, the oxygen you breathe, all came from stellar nucleosynthesis occurring billions of years ago in cosmic neighborhoods far from Earth. We represent the universe becoming aware of itself, matter achieving consciousness and developing the ability to study its own cosmic origins. Despite occupying one tiny corner of an infinite cosmos, humans have discovered fundamental truths about reality that apply across cosmic scales. we have glimpsed the true size of existence. The universe is not only stranger than we imagine, it is stranger than we can imagine, and we are here to witness it.